Hi, in this video we will work with, let's see, recursive descent parsers. So what we will do is to construct top-down recursive descent parser from the grammar we previously removed left recursion from. So I've written the grammar here. The programming language that we're going to use in this video is the Julia programming language. Similar procedure in Python I might provide in the future, but for now let's stick to Julia. I've added a link in which you can download Julia below if you want to try and run this code. Also, I've created a GitHub repository which you might also access this code. I might make companion videos where I implement the same parser in Python and maybe also C or MATLAB. Note that this video is not necessarily about how to learn or how to use the Julia programming language. The way I'm using it here is not necessarily optimal, let's put it at that. But it's rather about, okay, how should we think when designing or rather implementing a top-down parser for a given grammar. So we will do a recursive descent parser, that is LL1, that is left to right, we read, and we do the leftmost derivation. So let's construct one method for each non-terminal. We also have a method that called scan that updates our current token. I see now that I entered scan wrong here, so let's do this. The current token represents our look ahead of 1. So the parser, the k in LLK, is the look ahead which the recursive descent parser used to decide which production to use when it examines the next k tokens of input. Now it got a little bit too many comments here, so let's remove some. Yeah. Something like this. So first we're gonna create a global variable, and we can call it current token. Also, I'm going to create a global variable to keep track of our indentation level. So let's do it like this. Let's see. Furthermore, let's write a function to ident, that is function print and indent. Okay, spelling. And then we have stir, that is a string, then and. Yeah, let's just do it a bit sloppy here, so something like this. So now let's start with our recursive methods, or rather the methods that we're going to make use of. So let's start with the main method. And the main method will begin by calling our scan method, yet to define it. And then we simply call exp. Right. So let's implement our scan method. So our scan method, it reads from stdin, it reads a character, it puts it in res, converts said character into a string and puts it into current token. It also returns a string. Then let's write the exp method. We do it as follows, something like this. So we start by increasing our ident level by 1. We then print that we are on exp. We then call term and x prime, and look how similar that is to the rules we have up here. Let's see if we can highlight this in Emacs. You can see up here. And also I can maybe highlight this part as well. And then you can see what it looks like. See seems that I should enter a space here to make it a bit more yellow. And then we of course have ident, which goes to A, which goes to B, which goes to C as before, and num, which is a real number. We assume float 64, that is a float with 64 bits. So let's continue. So we defined exp, and we defined main, and we also defined a scan function. Let's now define a function for term. And a function for term, yes, that looks something like this. Term, and we have global ident level plus equals 1. And then we have print and ident. Seems that I have Swedish layout because I thought I was going to have English, but okay, let's stick with this. It's going to be some mistakes. And term, of course, if you look at it, should call factor. And then it should call term prim or term prime. Let's call term prime. Let's see. So term, factor, term prime. Yeah. This is about everything that it should do, and let's copy this line down here. So this is the function for term. So still nothing surprising, and you can see how similar the procedure is, or rather the code is, to the grammar that we have up here. So let's continue and define exp prime. You can see x prime here. So printed on x prime, and here we use our look ahead. So we check if the current token is a plus, and if and only if it is a plus, okay, then we scan the next token, we print an ident plus, then we call term and x prime. So here the parser use our look ahead to decide what to do next. And you can see it up here. So this is the rule for this. And then we have minus, that part is here. So we use the look ahead here to select if we're going to use this or if we're going to do this. Of course, currently we only print stuff, so the only difference it makes is we print minus or we print a plus, but nevertheless. And of course we also have epsilon, the empty string over here, and for epsilon we simply print, yeah, we have an epsilon. If we had done some syntax tree or something along those lines, or that we've done a calculator, here we would do the minus operation and we would do the plus operation. And here we will simply return because there is nothing to do. So let's continue and write, let's see, yes, term prime. And term prime, of course, mirrors x prime. It's very similar, except that now we have times and division instead of plus and minus. Otherwise it looks the same. But least but not least, we get into factor. Factor is our last method. And factor, you can see it over here. Let's see. You can highlight this stuff. Oops, daisy. That's wrong. Let's see. Highlight regex. Yeah. So factor here in green is what we implement now. So factor is either an exp in parentheses, an identifier, or a number. You can see it up here. So we increase the ident level as we did before. We print that we have a factor. If the current token is an opening parenthesis, we call scan. We call exp. And we call exp, and of course this will recursively call this entire chain we have over here. So exp, of course, we call term, which we call x prime, and so on. Then we scan again. And we expect it, of course, to be a closing parenthesis. If it's not, we will throw a syntax error and simply state that a right parenthesis is to be expected. Then we do something interesting. So here we use Julia regular expressions. So this we check if we have a letter from A to Z, or rather if we have A or if we have B or C and so on, all uppercase. So this creates a regular expression and then we match it. If we would get a match, we will return an object, but if we don't get a match, we would return nothing. So we check that it's indeed not nothing. Then we scan, we increase our ident level, and we print that we have an identifier. Then on the next branch, we check if we have a simple number from 1 to 9. thinking about it, it should be 0 here. And we compare that against our current token. We scan, we do this, and we print none as before. Then if we have nothing of these cases, we throw unexpected token current input. You can see here, because we have no epsilon case here for A and B or C, and the same with num. Num being something I added as a part of this extended the grammar with none. But it wasn't a part of the grammars which we transformed in the previous video. So, now I think we have everything, so we can simply call main here. And see if we can run this program. Let's see. Hi, so I made some corrections. For instance, I scanned at the wrong place in term prime, and also did so in x prime, as you can see over here. But now I think we're ready to run our little program. So, let's switch to a shell. Take PowerShell. And then let's just run it with Julia. So, we run it like this, and then we take A times B minus C. We get our tree here. So we go x term factor, and from factor we get an ident. Then we take term prime, we end up with multiplication. And then we have a factor, we have our ident B, and we have minus under x prime, term factor ident C, and then term prime goes to epsilon, x prime goes to epsilon, and x prime goes to epsilon. So, it seems that we did that correctly. So now let's just take A plus B plus C and see where we go. Yeah. So we have factor, ident A, term prime epsilon, x prime plus. Yeah. For our next video, we are going to add operations. So while we traverse the tree, we'll also calculate arithmetic expressions. So we'll actually get some results. So let's modify our program to allow for this.